the first thing we need to understand is electricity. Okay, so we know what electricity is and how it works and all that good stuff. We're going to explain tonight, basically, and it should be 30, 45 minutes. It's not going to be a very long class at all. So just kind of hang in there with me. Don't zone out. But basic electricity is going to be that fact that when current runs through a piece of wire, it creates a magnetic field. Okay, we know that. We know that from ELE 150, just basic electricity. We also know that atomic matter, atomic pieces, atoms make up everything. Right? It's our furniture. It's our metal pieces. It's wire. It's everything. Right? Some pieces are considered conductors and some pieces are considered insulators. If it is a conductor, it's usually like copper and iron, aluminum, that kind of stuff. It's a conductor. That allows electricity to flow through it. And the reason being is because that material, the molecules that make that up, have this thing with on the very outside of the atom is called a valence electron. I'm sure you heard that before. It's the outermost orbit. If something has between 3 and 4 electrons on the outside, it is considered a conductor, and it will allow electrons to bounce from one atom to the next. So if I was to excite or push with a magnetic field an atom, it would bounce from one atom to another until it eventually flowed as a current. On the other side, that we have insulators. So insulators are going to be rubber and glass and wood and all that stuff, right? Wood can sometimes be a conductor, but only because there's water inside, and not the water itself. It's because there's because water by itself is a perfect insulator. The stuff in water is what makes it makes it conductive. But water itself is actually pure water is not conductive. So the reason I'm telling you this is because with an insulator, things do not flow, and with a conductor, things do flow, and that's an important differential. So the first part we're going to talk about is static. Okay, so static is it's energy, it's electricity, but it does not flow. There's no movement. You're probably used to seeing when you walk across carpet, and you touch a doorknob, you kind of feel that spark. You're discharging yourself, right? A lightning storm, right? The cloud or the house, whatever one is the most negative, is discharging. It always goes from negative to positive. So, common question: does lightning go up or lightning goes down? Depends, right? Depends of which one's more negative. If the house is more negative, it has more electrons and it needs to get rid of them. It will discharge to a less negative something. If a cloud has a lot of electrons because of temperature and rain falling and all that stuff, it's nice, everything rubbing together. If it for some reason it becomes more negative, more charged, it will discharge. That's where you get thunderstorms from. So that's all static. The reason I'm mentioning this is because we use these things called capacitors, and capacitors are used for two different reasons in motors. One is to store power, like a giant spring. So if you were to electric spring, there's no actual physical anything in there, but if you pack enough electrons in there, it's going to build up and pack like you're compressing a spring. And then if you were to if the supply power was to dip down, it would release that back into the system. So we use it sometimes like a booster. If you have a motor that the voltage dips down because it's starting up and it takes a lot of current to get this motor running, it will require a capacitor to kind of fill that void. If you're into any kind of sound systems, you install things in your truck, your cars, they usually have capacitors on board because they have to store that energy. So when a speaker was to move or hit, it would have that energy. So you kind of see how a capacitor could be in handy. Also, what a capacitor is, or what it can be used for, is delaying a particular waveform. We'll talk about waves here in a second, sine waves. But basically, if you were to have let's say an empty bucket, right? Just a big, 5-gallon bucket, and you were to fill it with a garden hose, it takes time to fill that bucket up, right? It's before it actually allows it to be equal, or even start building up a positive, which is a large amount of electrons, a large amount of water particles in this case, it would take a while to do that. So the time it takes to charge a capacitor will offset or delay something by 90 degrees, sometimes 40 degrees, depends on the application. And this will all make sense a little bit in a few minutes. But it takes time to fill that capacitor. That being said, it will create a second wave in some cases, a sine wave. So all a capacitor is two plates with some kind of a dielectric in the middle. A dielectric is basically a giant insulator. It's just stuff, right? It could be a gel, it could be a material, it could be like a paper. Doesn't really matter. It's just some kind of a non-conductive material that electrons will build on, an excessive amount of electrons, and then when it's time to discharge, they will discharge. So it does take time to fill, and it does take time to discharge. So you get a delay out of it, and you also get the benefits of having a boost. Okay. So that takes care of static and capacitors. That's going to be that understanding, and that will come more in play when we talk about single phase motors later on. That's going to be our next, at the end of the semester, we're going to talk about single phase motors. That's why I want to kind of get this in your head now, so the rest of it is just nothing but labs, but they all make sense to you. All right, the next thing is magnetism. So magnetism, and just to kind of reference, static, you can find it in your book, Unit 3. Capacitors is Unit 20. So if you guys want to write this down, Unit 20 is where I don't want any homework, I don't want any practice problems, I don't want anything out of these chapters. I'm just telling you where they are in case you want to find them. But they're out there. So this is all covered in ELE 150, so you probably have seen it before. Just kind of refresh your memory. Magnetism. So what magnetism is when you have any material, the electrons inside, and in this case be more of the atoms, when you spin an electron on a valence, it has like a magnetic charge, a positive, negative, and you can almost think of them like a bar magnet. So I have a picture here in the book that is, and you'll see that this picture here on page 91, if you ever want to look, but you don't have to. With an electron, you're going to start seeing these electron spins, and these are basically, again, basically like little generators. They're spinning around each other. They're causing it to create a charge. So just to get past that, think of it like a little bar magnet. So think of this as a piece of iron, and the molecules within here are scattered. Now this is considered non-magnetized, right? This is not magnetized right now. All right, so there's materials that are either magnetized or not, and we'll talk about magnetized here in a second. So we just saw demagnetized, and that means everything. That means all the stuff in there is scattered. Nothing's lined up. There is no continuity of polarization. Some materials can't be magnetized. All right, these are called non-ferrous metals. So non-ferrous basically means they can't hold a magnetic field, or they can't be magnetized. So something like a stainless steel, the molecules are so tight inside there that they just can't move. And if they do move, it's very, very slightly, not enough to get them all lined up in a line. So stainless steel, especially a good stainless steel, is not magnetic, or can't be magnetized. It's non-ferrous. Aluminum is also non-ferrous, and it is very soft. Copper, same thing. It can't be magnetized. The reason is the material itself, and I'll explain wires here in a second. But material itself, if you have a big block of copper or aluminum, you can't make it magnetized. And the reason is because it's too soft. So the energy it takes to get all those particles and everything in a line and going in the same direction to become magnetized, as soon as you release whatever you're trying to do to make it magnetized, as soon as you release it, they're all going to kind of slump back into their old way. They're going to have memory because the material is way too soft. It just can't hold that form. So too soft or too hard, non-ferrous. The sweet spot in the middle, those are called ferrous metals. So those are going to be your irons and that kind of stuff, like your steel, right? Your basic steel and your iron and all that stuff. Those can be magnetized, and they magnetize very well. Within that, there's different layers. So they have different things called, if you have something that is very hard to magnetize, it has a reluctance, and that's a term. So if a metal is reluctant to be magnetized, which means it's like a stubborn child, right? It doesn't want to become, it's not going to do it. It's reluctant to become magnetized, so those molecules have a hard time getting lined up. It's a high reluctance. A low reluctance would be the exact opposite, like too soft. And then we have permeability and saturation. Saturation is it gets as magnetized as it's got to be, right? So certain materials can only line up so much before they can't be magnetized anymore. They're not perfect, but they're closer than they were. They're kind of all pointing in a general direction, but they're not straight up and down. And the reason I'm mentioning all this stuff is because it's good to understand what's inside a motor. And in order to understand how to troubleshoot a motor, how to fix a motor, you need to know what the individual parts are doing to their basic level. So the best technicians, the best engineers, the best electricians are going to be the ones that understand every single part of a mechanism. Not just hooking it up, but actually like how to diagnose it and why it's doing what it's doing. So that's why I'm kind of going through this stuff one by one. All right, so we talked about demagnetized material. So a magnetized material would look something like this guy right here. He's a little farther out, but I'll kind of show you. Right, so everything's lined up, everything's in a place, and everything is all in order, kind of in line. Now this is a very dramatic exaggeration, but you get the idea. If you were to snap this in half, it becomes it would break into smaller magnets and so on, right? So it is that material it's magnetized now. So if you ever had a screwdriver that had the tip became magnetized, that's what's happening. All those particles are all lining up in the right order to become magnetized. And that is a stainless steel type. It's not a pure stainless steel. It's got enough molecules in there to become magnetized. So that's why you can magnetize the tip of a screwdriver, even though it is stainless. So we talked about that. Now we're going to talk about electromagnets. So we understand what a magnet is. Okay, so we have permanent magnets, natural magnets. So like a lodestone, dig it up from the earth, it's a magnet, it's there. Or we have a chemical made, so this is like your neodymiums and all that stuff. It's really, really engineered magnet types. Those can be made by man. And then we have electromagnets. So electromagnets are things that can become magnetized and then all of a sudden not be magnetized. So when you run current through a conductor, like I was saying in the beginning, when you run a current through a conductor, that wire by itself, the current flowing through it creates a magnetic field called flux. And the flux is basically, you can imagine like a little force field of little waves coming off the thing. Very, very, very tiny, but they're just enough. So if you ever had an old car or anything else and you had a loose wire, loose ground, and you heard a kind of a whining noise in your speaker system, or if you had like a hum in your sound system or in the house or whatever, you have like a electric hum, like a real low frequency, that's inductance, right? That is the magnetic field off your wires in your wall or the wires in your car inducing onto other materials or coils. And in that case, you're hearing it because it's inducing onto a speaker coil, which is making the driver move, which is making sound. That's why you're hearing that noise. The wires itself do not make the noise. So if you have a straight piece of wire and you run current through it, it will produce that magnetic field. The cool part is the more current you put in, the larger the magnetic field, so we can control it that way. But also if we wrap it in a coil, in a loop, around, let's say, like a toilet paper tube or something, like a hollow tube, right? It becomes an electromagnet. This is called a air core electromagnet. So this is like your doorbells and stuff like that. If you ever push like an old doorbell and you're ding ding, right? That is a plunger that is sitting inside of a air core electromagnet, and then when you push the bell, you're closing a circuit, you're creating a magnetic field, and it's shooting a plunger out. When you release it, it shoots back with a spring and hits that second tone. You ding dong, right? So that is the noise that you're hearing is the gong hitting back and forth from an electromagnet. Solenoids are the same way. With transformers, we'll talk about transformers in a little bit another day because it has to do with another type of motor. But just understand that if you take any kind of wire and you wrap it around a tube with air, or it could be a piece of plastic or anything that's non-ferrous, This is called an air core electromagnet. So if you take that same thing and wrap it around something like a piece of iron or a screwdriver or something with a metal iron core, you're going to get a iron core electromagnet. All right, so this is where we're getting into the motor world now. So within the motor, these things called pole pieces. Pole pieces are basically just chunks of metal, nothing special about them. They are laminated for eddy current. We'll talk about that in that chapter. But basically, they are sheets of metal that are all pushed together, and they have a coil of wire wrapped around them. So by wrapping them, the magnetic field gets stronger. So that's good. And also by increasing or decreasing the current, you can make how strong or weak that magnet becomes. Also, another cool thing with electromagnets, depends on which way you run the current. It depends on which way is north and which way is south. So if you run it one way, it'd be the north, right? And you run it the other way, the other side becomes north. It all depends on which direction you're running the current through that coil. And they call it the left-hand rule. If you take your left hand and you were to wrap it around the direction of the current, your thumb should be pointing to north. That's a good rule of thumb. So this makes it where you can now create a magnetic field out of something that wasn't magnetic a few minutes ago, which means you can turn magnets off and on at will. You can also reverse a polarity of a magnet. And if you know, if you had a refrigerator magnet, you can't do that. A permanent magnet, a natural magnet, you can't do that. It never turns off. So an electromagnet has the ability to go off and on and reverse its state. So with these in a proper order, we can actually get these things to push or pull something around. And that's when we get into our motors. So the next part, and the last thing we'll talk about today, is going to be, I told you it's going to be short. The last thing we're talking about is going to be power generation, and we're going to get into this a lot more in the chapters, because we're going to talk about DC generators and AC alternators in future chapters. And actually next week we're talking about generators. So the basic premise, and I'll just kind of explain this and I'll leave it where it is that in the power company, when they try to create power, electricity, and that's a misnomer as well. You don't create electricity. Electricity's there. You take a piece of wire, sit it on the desk. It has all the electrons it needs inside there. You are exciting the electrons and pushing them and causing a flow. You're creating current. That's all the thing you're doing. So if you don't have electricity and you need to make electricity, electromagnetic goes both ways. You can make an electromagnet or run a current through a coil to become an electromagnet. So you create a magnetic field, or you can take in a magnetic field and create current. So you can do either way. It goes back and forth. So and we just talked about a minute ago of running a current through a coil, causing it to create a magnetic field. But if I already had a magnetic field, like a permanent magnet or an electromagnet, and I ran it past a coil, what's going to happen, that magnetic field is going to it's called cutting the flux. It's going to cut through the flux, and that means the wires that are wrapped in a coil, you can imagine the kind of wires sitting here, and you imagine a magnet going past it, that those flux lines are kind of like, imagine like a little circle, and as it goes past, it's cutting through these coils, which means you're putting energy onto these coils, which means you're exciting, and that's a term. You're exciting the electrons, and electrons are actually moving slightly. Every time it goes around, it pushes them a little bit more through the wire, through the conductor. And every time it happens, it pushes a little more and pushes more. So it's kind of like a little pump, right? Every time it pumps, it pushes the water or something like a little farther down the pipe. Same thing here. Every time that magnet goes past, it pushes the electrons a little bit farther down. And the stronger the magnet, the harder it pushes, right? So you create more current, more current from the device. All right. So if you take that device, let's say it's flat, and I take the magnet and I go past it, I'm going to create this spike. All right. So 0 volts, and all of a sudden I have a spike at whatever volts it produces. When the magnet comes off it, it dips down to 0. So you kind of get this up and down. You put it on a linear scale, meaning time, because time never stops. Voltage starts at 0, and it's going to increase to the height of whatever it is, and then as it goes away, it's going to die down to 0 again. So you're going to get this bulge. Well, if I take two coils and I take one and wrap one direction and wrap one another direction backwards, when I cut through the first one, I'm going to get a positive because they're pushing in one direction. When I cut through the second one, it's going to send the current back the other direction, negative. So if you do this, if I have two, one this way, I'm going to get this positive, negative, right? Just that one movement by two coils. Now we've created this pulse, this positive and then negative. It crosses the negative line. If I take that mechanism, instead of being flat, and I put it into a circle, all of a sudden you get this wave. It starts at one point, it increases like a diagonal to a point, and then back down, and then hits zero, and then goes negative, and then back up. So we call this a sine wave. So it's sinusoidal. It's the typical symbol you see for electricity. See that little squiggly line? Sine wave. If you take that sine wave, right? So sine wave looks like this, if you look at it, and if you were to flip it around, it creates a circle. Because when you create when you generate power, you are using a alternator or a generator that is spinning in a circle. So that's why when we refer to electricity, we refer to it in 360 degrees, at the start being 0, the top of the first peak being 90, where it crosses zero line, 270, and then 180, I'm sorry, and then 270 at the negative, and then back to 360. So from point A to B, C, D, and E, we have created a full positive, negative, and that has completed the circle. So when we refer to electricity, we use angles. And I'll be doing a lot in this class because we have angle shifts. Some motors use them, some don't. All depends on the type. So hopefully that explains when you were to flip that backwards, it becomes a circle. But because time is moving and can't stop, we show it as a sine wave because it's not, that same point has to keep moving. So a better description of why that is the way it is that if I was to take a piece of paper and I had a bicycle wheel with a marker on it, and I spun the bicycle wheel, right? And I took the paper and it went linearly across it, you're going to see this wave. Because as it goes up, the paper's moving, right? It went up, and then it kept moving, and then went down, and then back up. So the marker's doing this, but the paper's doing this, right? And then on the paper, you'd have a squiggly line drawn. So that's how we get sine waves. That kind of explains that whole thing. If we take multiple of those pole pieces, and we have 3 different sets of coils, we get to something called three-phase. So if you ever heard of three-phase power, three-phase electricity, three-phase whatever, that is when each of the waves are 120 degrees off from each other, their starting position. That means they're all in different positions at any point in time. So 2 of them are providing power when the third one is not, and then vice versa. As one dies, that one positive, and so on. So that's where you get three-phase power. So that's going to come in handy when we talk about AC motors, because the first part's all three-phase. The capacitor part will come in handy when we talk about single-phase, and then the whole magnetic push-pull will come in handy when we do our DC generators and DC motors. So you're going to hear some of this again, but I just need you to kind of understand the basics behind it, because I want it to become clearer if you guys are confused at all, or you didn't pay attention to ELE 150 and you didn't have the chance to really get these concepts. These are the ones that make sense, or that make everything happen in the motor. So the motor it won't work unless you have these components doing their thing. So that's it for the lecture. Just some footnotes, and I'll let you guys go because I really have nothing else for you. The reason we don't have, we're not doing a lab this week is because my hybrid class, and I'm sure you've seen all the videos of all the confusion, my hybrid class, they do not have labs until next week. And I want to keep you guys in check, because it just makes my life so much easier. So what's going to happen is when they start their physical lab, we will start our digital lab at the same time, and we can both do the same thing. I'm not trying to do 2 different lessons the same day, because once we're done with theirs, I got to do yours. So that's the reason we're not doing one this week. So last week was safety. This week is going to be just review. And then next week, we're going to talk about DC generators. And then we're going to have our lab and everything else. So for the lab, make sure that you guys have your software. And again, it's all online, so you don't need to download anything. But let me move this over, and you should see. Yep. So this is the one I was talking about. So if you don't remember what it was, it's the lvsim.labvolt.com. It's any web browser we're bringing up. This is our lab world, right? And if you need that code, let me know. If you have that little box that pops up, please let me know, and I'll give you the code, and you guys can get in. But everything we do in the labs will be right here. So we start going through and dealing with motors and stuff. We're going to be pulling motors off of here. We're going to put motors into spots. We're going to power supplies and all that good stuff. So all our labs from our lab book will be in that position. What else? Make sure that you have your textbook. Make sure you have your lab book. If you don't have it, please get it in. Because I'm not going to wait for it. I'm going to keep moving, and then you're just going to fall behind. And I really don't want that to happen. So make sure you guys have your stuff, have your lab book, have your stuff. And besides that, I mean, everything's on Canvas. Homework, quizzes, everything you need will be on Canvas. And all you do is just go down the list and check everything out. If I put a video up, watch it. It may be more geared toward the other people. You're going to hear it again, maybe. But, you know, you might be able to pick some things up one time or another. But your stuff's going to be laid out in line with everybody else's, and you're just going to go down the line and say, okay, today's quiz is this, and this is my assignment, and this is my homework, and this is whatever, right? But this week here, there's nothing. But the only thing there is a video, and it's exactly what I just said right now. So, again, if you don't understand something, you just want a clarification, you can watch that. So